Yeah, it's fine, Aaron. Let's see, do I have audio? I can see my green mic coming up. Can you all hear me? Nice. Let's see here. Okay, do I have the recording going? We are recording. That's good. All right, some announcements before we get going. The exam I just posted. Let's see, am I sharing? Yeah, I'm sharing too. So I just posted like an hour ago feedback to your exams. So if you go into the Dropbox, you should see graded. What's that? I don't know if Jacob had a question or unmuted himself accidentally there. So you should see in the D2L Dropbox, you should see graded comments on your exam. And then grades should be up to date. Here's a YouTube video of me working through it. I did make a small mistake there. I don't know why. And then I would like to see another reflection. And I feel a little bad because I know like you have all this other work to do and it's just one more thing to do, but it's so valuable for you to like look at your exam, kind of think it through, because we're gonna have some of the same content again, not just, you know, because we're assessing line integrals again, but because 17.4, 5, 6, 7, and 8 uses a lot of the double integrals again. It uses a line integral again. And so to make sure you're reflecting on what you did, and so you understand that content moving forward is worthwhile. So we're still going to do that reflection like we did for the last exam. This is going to go in the quiz category. So it's kind of a free 10-point quiz, because I mean, it's not free, but it's not graded. As long as you do the work, you get the points for that. Let me remind you what that reflection looks like. So the first part is error analysis. For any problem you lost points on, you kind of write about what's the mistake that you made, or maybe multiple mistakes. You might have to watch the video to get that. Sometimes my comments aren't clear, but like sometimes, you know, me circling something, you're like, okay, well, that's where my mistake was, but I don't know, like I don't know what that circle means. So you might have to watch the video to really see that, but I want you to write about your mistakes. That's part A. If you want to think of an error type, that can be useful as well. Like, you know, this was an application error. I knew I needed to convert to these from dy dx to dx dy, but I got stuck in there or something like that. And then watch the video and redo the problem again correctly after watching the video. So that's the part where, like, hopefully by the end of this process, you will also like fill any gaps that you may have had while taking the exam. And then the second part is an overall reflection. So what do you think are the reasons for your grade? Feel free to put, we're in the middle of a global pandemic and I'm trying to work and do all this stuff at home and it's stressful. That's totally valid. Whatever you want to put there, that's totally up to you. And then kind of, there were 3 specific and realistic actions. It's really just for the last week. Like, what are we going to do for this last week before the final to make sure we do our best on that? Yep, and you can just turn this in. I have this instructions from when we were face-to-face in my other classes, turning in a separate sheet and paper clipped and blah, blah, blah. You need to do any of that. You know the drill. Take a picture, upload a PDF. There's a Dropbox all ready for that. And I thought we should really have this done before we're talking about before we're working on the final. So I put Sunday as the deadline for that, 11:59 p.m. Sunday. Hopefully that'll give you, it's Wednesday now. I'm hoping it'll be like a half-hour exercise. If you really struggled on the exam, I suppose it could take longer than that. Some people did really well, and you can probably knock it out in 10 minutes. So that's the time it takes is going to be up to the individual. Does anyone have any questions about the reflection? Okay, so again, grades should be up to date. If you have any questions about your grade, feel free to let me know. Let's talk about our schedule. We are going to try to have a super productive day today. We're going to try to talk about homework questions and practice some stuff from 3 different sections. 17.5 is actually pretty easy, but 17.4, Green's theorem, there's some big stuff in there, and then 17.6, surface integrals, also a heavy hitter. And then we'll have one last quiz over those material, and I'm going to try to keep the quiz a little bit lighter than I would if during a normal semester. That stuff would have taken probably 2 weeks, maybe a week and a half. So I'll try to do some of the more basic questions. Some of the homework ones are pretty challenging. Some of the ones in the notes are really challenging. So we'll try to keep the quiz a little tamer, focus on some of the main ideas. And then next week, we're not going to have class on Wednesday. We're going to have a Monday class instead, focus on our last 2 sections of content. The final exam will be released after class, and then it'll be due by the end of the semester, literally the absolute end of the semester. The semester ends on Wednesday, so 11:59 p.m. Wednesday will be the deadline for that. Any questions? Any questions about timeline or what's coming up? All right, I'm not.
Actually, where can we see our grades after you post them up so I can take a picture and send it to COD?
So what I will do, I should do this right now. I will edit D2L. There's 2 places. The D2L is going to be fastest. But I will edit D2L so you can, like, if you don't change this, okay, I already did fix it. Look at that. Look at me thinking ahead. So I set the course end date to actually be the end of May, so you can still log in after the semester ends and see your grade. So that'll be where it'll be posted first, but that, I don't know if CD will accept that, you know, like, because that's not your official grade. So you probably have to go to the portal, the, what is it, portal.elgin.edu, and log in there to see it officially. My guess is they will probably need that, but you could see your grades and kind of show, hey, this includes the final, you know, and I don't, is it like a person you're talking to?
That's a prerequisite.
Right.
Yeah.
So prerequisites, they usually need to see the actual transcript, which means it needs to be officially recorded. So that would.
Well, they asked for right now. They just asked for the unofficial transcript to show that I was on the course, and they said all I just need is a grade with my name on it. So
you could probably get that from the grading tab in D2L and
yeah,
send them a screenshot or something.
They said they said I got till the 21st. So I'm hoping I got a 3-day window. So it's the 18th, I think. But
it'll be fine. It'll be fine. Yeah, and I'm gonna be. I honestly, I want to be done. So once the semester's over, I'm gonna work really hard Thursday and Friday to get all the grades in, so I can be done. So
okay,
it's probably not gonna be Monday. Yeah.
Okay.
Oh, that's very selfishly motivated. That's. All right. Let me know if you do have any other questions. Oops, got my email up there. You don't need to see my email. Let me know if you do have any other questions about timing or anything. I feel like there was something else I was going to say. Oh, I had a meeting with my dean on Friday, just kind of FYI, planning ahead for fall. And I would be surprised if we went, based on that meeting, I'd be surprised if we were on campus in the fall. I would plan for online in the fall as well. COD, Harper already went online and COD is about to, and so I just FYI, I kind of plan on that. But I would plan on also a full slate of offerings in the fall. So once the college makes that decision, we'll be putting in proposals to make every class we can online. So just FYI. Okay, let me open up the homework. I have plenty of examples. I posted them in D2L, the 17.4 and 5 practice, and then there's a 17.6 practice. Those should be there. I get confused sometimes with the two sections, but there's, yeah, 17.4 and 5, and then 17.6 examples. So we can just do those if you would like. There's lots of really good stuff there, but I can open up the homework. It's so hard to refocus yourself when you had this big exam last week, but I know people were watching the videos because I got some emails. So let me get the textbook up. It's kind of hard to flip back and forth. So if you don't mind, can we start with Green's theorem, 17.4? You can type requests in the chat or just unmute yourself. Does anyone have any specific requests?
Question 15 on 17.4.
Okay. Oh, it's in the first part here, sorry. I accidentally clicked to start this other program. Ay, that's annoying. Sorry, now I like to do my screenshot. Okay. I learned a cool new trick though with my tablet and my pen. You like click the back, and then it changes to let you do to capture the screen. It's kind of cool. Bloop. All right. Any particular part of this, or do you want to just go over the whole thing?
The whole thing.
No problem.
I don't even know what I got. I had that it was not irrotational, and
Yeah, I don't think it is.
that was about it.
Okay, no worries. All right, so curl, gotta have good notes here in this class. Go back to 17.4. Oops, 17.4, zoom in a little bit. So this partial derivative of g with respect to x minus the partial derivative of f with respect to y, that is the curl. That is the curl for a two-dimensional field. So, oops, going back to the example, the curl of this field will be the partial derivative of its, where's our field? Oh, it's way over here. I feel like I need to zoom in, like this is really small. I am getting old. I got to tell you, I had, wait, my eye appointment, yeah, no, I was doing it the wrong way. G with respect to X. A couple of years ago, and he was asking about, you know, how's your vision? Are you noticing any differences? And I'm like, yeah, you know, sometimes reading things up close, it's getting a little hard to read. And so he did the thing where you like flip the little glasses down. He's checking my reading, my close vision. And so he's like, all right, here's what you're right now. Like, this is what your prescription is now. And I'm looking at it, I'm like, yep, kind of hard to read. So he does some of the flips, like what it would be for reading glasses. He's like, how's this? And I was like, oh, that's so much better. It's like it was obvious that it was not good. Anyway, so what we're going to do here, the G and the F from the curl are from the field. The F is the X component of the field, and the G is the Y component. So we're taking the partial derivative of the G component with respect to X minus the partial derivative of the F component with respect to Y. That's 1 minus 0, so that's 1. So that's the curl, and you're right, it's not 0. So the field is, this is like a double negative. I feel like math has a lot of this. It's not irrotational. I feel like you should just be able to say like, well, then it's rotational. I don't know. All right, so that's A. And then B, we need to find parameterizations. We're given the region here, y is greater than or equal to x squared. So that means this path is x squared. and then y is less than or equal to x. So this path is y equal x.
I got x equals t and y equals t squared.
That's the easy one for C1. That sounds good. For
Yeah,
C1,
the next one is where I got stuck.
it's when you have to work backwards, those are usually the ones that throw people off when you have to, because the orientation is really important. So, what the heck? So yeah, I would go t and then t squared. Yep. And I would use this whenever you have y as a function of x and you're trying to go left to right. When you're trying to go left to right, then just let x be equal to t and let y be equal to whatever the function is. And then we do need to specify t here, and it would be from 0 to 1 because that's where they intersect. They intersect here at the point 1, 1. Then to go backwards, I mean, it's a line. You could use the vector form for a line where you have an initial point and a directional vector, which would be -1, -1. You can make it a little simpler than that. So for C2, R2, R2 of t. Let's see, we need x to go from 1 to 0. We need to go backwards. So instead of t, we can go 1 minus t. And what that will do is when t is 0, x is 1. And then when t is 1, x is 0. And so that makes it, that's what makes it go backwards. And then again, y is equal to x, so you just make them the same. So what I usually do personally is I manipulate the x. If I can get y as a function of x, I manipulate the x and then just let y equal whatever the function of x is. Oh, and we need a t interval for that one too, but that's also 0 to 1. And not always. There was a line integral on the exam where it wasn't. You didn't need to have it be 0 to 1. But for these two particular ones, that's probably the easiest. All right, so far so good?
Yeah, I follow.
Okay, good. Not seeing any other questions either. So now what they're going to try to do here, this checking for consistency. They want us to do both the line integral and the double integral in the circulation form of Green's theorem and check for consistency. This is what Green's theorem does, is it gives us two integrals that are equivalent. So let me grab this as well. So this is the circulation form. There are two forms. This is the circulation form. Okay. And on the left-hand side, we have the line integral. And it has it both in the vector form and in the differential form. And then on the right side is a double integral over the region. And you integrate the curl over the region. This is what Green's theorem says. It has two versions, but this version is the circulation version. What it's saying is the circulation around the outside of a region, if the region meets certain conditions, the circulation around the outside of it, along a path around the outside of it, equals the double integral of the curl inside of it. So this question, letter C, is asking us to do both of those and show that they are in fact equal for this particular example. So this is a closed line integral, meaning our path comes all the way around. Now the downside on this one is it's actually two line integrals because we have two paths. So I'm putting subscripts there, C1 and C2, path 1 and path 2, and then I'm writing it as DR1 and DR2 for the two different R's. I feel like I need my F again, just recopying that here. My field was 1 and x. Now we're going to do the integral of the field over that path, So in place of x, we will put the x value from our path, whatever the path is. All right, so path 1, it was 0 to 1, and the field will be 1t. That's the x value from that R1 path. And then dot product with r prime of t for R1, that would be 1, 2t dt. So that 1, 2t, that's the derivative of R1. Plus the integral from 0 to 1 of 1 and then 1 minus t. Again, that 1 minus t, that's the x from that second path. And then dot product with R2 prime, which is actually just -1, -1. And now we need to take some dot product. So 1 times 1 plus t times 2t plus, and then you go from 0 to 1, 1 times -1 plus 1 minus t times -1, which I guess is -1 plus t. One minus t times -1. I want to pause right here. That's the hard part. The integral itself is a Calc 1 integral. Line integrals end up being functions of t, and so it's just a Calc 1 integral. So this, we've done the hard work so far. Any questions so far about how we got to this point?
No, the only part where I was stuck is just that how to get the R2.
There are two. Cool. Yep,
Yeah.
that's fine. We can keep going. Well, you know what? I'm sure you can do this. I'm sure not. I don't mean you, but I mean I'm sure everyone can do this. Let's look at the
Yes.
double integral. Let's look at that one. The double integral over the region of the curl of f dA. So that's a double integral. And the curl we said was just 1. Oh, this is kind of interesting. So it's just the area of the region. But let's set it up. Let's see. We'll go dy dx, and y goes from the parabola up to the line. So y goes from x squared up to x. If we're doing dy first, we're adding vertically first, and then x goes from 0 to 1. And if we did everything right, these should be equal.
I'm sorry, how do you get x squared again?
Well, the region, I'm going to just redraw it here. The region was y equal x squared and y equal x.
Oh, and you go from underneath and then go from underneath to the top, right? Oh, okay.
Yep. You have your representative piece here. And so you go from bottom to top, and so that's x minus x squared, or if you're going to integrate, it'd be from x squared up to x. And then you're adding them along in the x direction from 0 to 1. This is honestly, like what we're doing right now is the reason why we learned double integrals. It wasn't really to find the area of a region. It was really to do stuff like this. I should be pointing this way, because aren't I in like the top right corner? I don't know. I'm all disoriented. Sometimes it flips me, so I don't really know which way I'm pointing. The second one, I think we can probably not do that. It's the same idea. Compute the two-dimensional divergence, and then use the flux form to explain why the outward flux is 0. So I don't know. I mean, does anybody? We could do that. It's a little different from C. would anyone like to see part D?
I'd rather spend more time on the surface integrals, to be honest.
I think that's a fair point. All right. If you would like to see that one, you could email me and we could talk about it off to the side. That's fine. All right, so this is a good Green's theorem. A little aside here, I was thinking about the final and kind of, it's so different testing in this environment. I almost want to remove the temptation for you to look at your notes and instead just write an exam with that assumption that the notes are there and available. And so the consequence for that is then the focus is more on this process that we did here, like the setup process. Because if you have all your notes in front of you, and then doing an integral itself is not really, I'm not really learning what you know in your head. But if we're focused on a process about, hey, set up a line integral, set up a double integral, and asking you to kind of and set up some of those concepts, it really gets at what you've understood. You can't just like copy a previous problem. So I think we're going to focus more on making sure that we're assessing more concepts. And I think I'm just going to write that test, assuming that you have your notes available. If I were you, I would probably still make a very nice organized formula sheet so you're not flipping. Right? You could spend a half hour flipping for stuff. So I would still have a nice formula sheet, but I think I just want people to like know, like, okay, well, you could use your notes if you want to. And then we'll focus more on kind of big picture setup questions. All right, let's talk about any other homework questions. We're still in 17.4 for now. Any additional requests here? All right, I'm not seeing any. I do have some examples, so we'll do those together. And if you haven't gotten to this, I know if you haven't gotten to any of these videos, you're probably a little stressed out. Hopefully we can do some examples to ease that a little bit, but you are gonna need to watch them to really feel prepared. Any 17.5 divergence and curl questions? No questions there either. All right. And 17.6 then, I know, Christian, you wanted to see some examples. Did you have homework questions that you wanted to look at, or do you want to just do some examples?
Some more examples.
Okay. Any requests while we're in the homework here?
To be honest, I haven't done the last four, so I've done the video. What was it? Yesterday?
Yeah.
So
yeah, it's a lot.
Really done yet.
It's definitely a lot. It's definitely a lot. All right, let's jump in then. Let's do. If you want to follow along with the ones I'm doing, I just pulled some from the homework here, and they are under the content browser, Unit 5. I have some 17.4 and 5 examples, and then 17.6 examples. So again, the main idea for Green's theorem, there are two forms of it. There's the circulation form, which says, this is the, it has to be a closed line integral. It has to be around a curve that's closed. It comes back around. And it's f dot with dr. And that is equal to the double integral over the region of the curl, which we said was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And that's one version. That's the circulation form. And then we should have a flux form in here too. Flux form. So this one is the outward flux, so you can imagine like a circle, how much flow is there going perpendicular across this curve. Let me find the middle version of that one too. Keeps like zooming back out. Sometimes this differential form is easier here. So f dy minus g dx. It's just the differential form, but sometimes it's easier to use than trying to find a normal vector and do the dot product and ds and all that. So sometimes the differential form is easier here. And this is the double integral over the region of the divergence, which is the partial derivative of f with respect to x plus the partial derivative of g with respect to y. So you're going to want these two forms written down. And make sure you understand what the components are. So the circulation is how much of the field is in the direction you're traveling, kind of how much you're being pushed. We did that as a work calculation. It can represent work if the field represents a force. And then the flux form is kind of how much is moving across the surface, like normal, or not surface, this is two-dimensional. So across the curve. It's normal to the curve. So these are pretty straightforward examples from this section. Doesn't mean they're easy, but of this section, compute the curl, evaluate both integrals in Green's theorem, and show that they're the same. So I'm going to switch to blue here. So the curl of a field is this partial derivative of g with respect to x minus the partial derivative of f with respect to y. We have our field, let me recopy it off to the side, is negative 3y and 3x. And so that's the negative 3y is the lowercase f we're talking about, the x component for the field. And then the 3x is the g, the y component. So we want partial derivative of g with respect to x, that's 3, minus partial derivative of f with respect to y, that's a negative 3, so we get 6. So that's letter A. The two-dimensional curl is 6. So it's constant here, which is actually not always the case. Often that will depend on x and y. It'll change depending on where you are in the plane. All right, now we're going to do the two integrals. So first, let's do the line integral. And we need a path. Ooh. We have a triangle with vertices 0, 0, 1, 0, and 0, 2. In Green's theorem, one thing about the path is it's always oriented with the body on your left. So it's always oriented counterclockwise. Always a counterclockwise orientation. So unfortunately, we're going to have to split this up into C1, C2, C3. Now C1 and C3 will be pretty simple because one of the components is 0. So that's nice. C2 will require a little bit of work. So C1, maybe I'll just do the R1. R1 of t would just be t and 0. T goes from 0 to 1 because it's just the x is increasing and the y is always 0. R2, let's see, this would be the equation y is equal to negative 2x plus 2, right? Negative 2x plus 2, y-intercept of 2, slope of negative 2. So here's what I would do for this one. This is what I hinted at for the homework question, 15. I would focus on the x and how I get the x to go backwards from 1 to 0. Do you remember how I did that? Anybody remember how I did that? See it on here?
You're subtracting the t.
Is 1 minus t. Yeah, that makes it go backwards. If you do 1 minus t, then when t is 0, it starts at 1, and when t is 1, it goes to 0. It makes it go backwards. Makes it go backwards. So we're going to do that here, 1 minus t, and then I'm just going to plug that x value into the curve. Negative 2 times 1 minus t plus 2. And then I'll simplify 2t. That's it. I guess that makes sense because when t is 0, y is 0, and when t is 1, y is 2. Done. Okay. And so that one also will go from 0 to 1. And then R3, let's see, x is always 0. X is always 0. And then y, I want to go backwards now. I want y to decrease. So I'm going to do the same thing, but I'm going to do 2 minus t. And then I'm going to make t go from 0 to 2. And that'll make it start at 2 and end at 0. Okay, questions so far about parameterizing? Okay, this is like an underemphasized thing in Calc 2. I'm guilty of it as well. It feels like, well, like you forget about how important it is in Calc 3 to be good at parameterizing curves. Okay, so we're gonna have to do 3 integrals here. Okay, the field is negative 3y. So for curve 1, that's negative 3y. That's nice, that's 0. And then 3x, and x is t. And dot product with r1 prime, which will be 1, 0 dt. And that one's from 0 to 1. So that's all for curve 1. Again, what I'm doing is I'm taking the y component of the curve and substituting that into the field. Because the x component was negative 3y, and on this curve, y is 0. And the y component is 3x, well, on this curve, x is t. So that's why there's a t here. And then the 1, 0 is r1 prime of t. Okay, we got 2 more. That first one's actually really nice if you multiply it out and think it through in your head. Actually, it's nice. Then we have 0 to 1. Again for the next one, and it is negative 3, and then y is 2t, and then 3x is 1 minus t. And then the derivative, r2 prime, will be negative 1 comma 2 dt. That's all for C2. Then the last one, 0 to 1, negative 3, the y component is 2 minus t. And then 3, the x component is 0.
Wouldn't it be 0 to 2?
Oh, it would be 0 to 2. Yep. I was thinking about that earlier. I was like, okay, got to remember, they're not all 0 to 1. All right, and then the prime here would be 0 and negative 1 dt. That's all for C3. Now that looks really bad because there are 3 line integrals. How about somebody who hasn't answered yet today? You can type in the chat if you don't want to unmute yourself. Why does this not actually end up being so bad?
Because the first and the second integrals are negligible.
Could you say it again? The first
And the second integrals, after you do the dot product, they both just become the integrals of 0.
Oh, I didn't even think about the second one. I know the last one does too, right? Don't C3, doesn't C3 also equal 0? Because you have this times 0.
Oh yeah, I was saying the first and the third one.
Yeah, first and the third. So C1 and C3 are definitely 0. And then does the middle one too? I didn't even notice that. I don't think so. So the first and the third actually end up being 0 after you do the dot product. So that's not actually as bad as it looks. And then we have 0 to 1, and let's see, I'm gonna need to, I can't do this all in my head. Negative 6t, 3 minus 3t, dot product with negative 1, 2. And yeah, not gonna be 0, but it'll be pretty simple. That was negative 1, 2. So I have 6t plus 6 minus 6t dt. My Calc 1 students would say, all right, I'll take it from here. I got it. The integrals are usually not hard here. It's usually getting that set up that's the most work. So that's just 6t from 0 to 1. Christian, question?
No.
No? Okay, you don't sound convinced. You're like, oh,
No, it's
maybe,
just a
but
lot of work just so it can
right?
become that.
I know, that's just mean. Like, wait a minute, all that work. Now, you might wonder, like, wait a minute, this is what we got up here for the curl. Careful. Yeah. There's a reason why they're equal, but a line integral should not equal the curl. That's not what the theorem says. The theorem does not say the line integral equals the curl. What it says is the line integral equals the integral of the curl over the region. So that's the second part that we need to do. We also need to do the double integral of the curl over the region. So that's the double integral over the region of the partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. And we already did that. That was 6. That was 6. Now, in this particular case, that 6 is a constant, and you can just pull that constant out in front. In general, if I ask you to find the double integral over a region just of dA, what are we finding? I feel like I need to go back in my notes. Ooh, how far back was that? Double integral, 16, 2?
Find the area.
Yeah, you're just finding the area. It's in here somewhere. I don't know. Somewhere in here, if you do just a double integral over the region, it is indeed just the area. Yeah. So all we need to do is find the area of the triangle, and its base is 1, its height is 2, and so you get 6. So they are equal here, that the 6 was equal to the curl, but only because the area was equal to 1 here. That's all. That's just coincidental that the line integral happened to be the curl. But we didn't, this isn't a proof of Green's theorem, but it does kind of verify, yep, Green's theorem is consistent here. The two integrals give you the same result. Any questions? Any questions on the rest of that one? All right, let's see how, I don't want to do this flux one. We'll see how long this one takes. So we're going to do the divergence here in letter A, compute the divergence. That's the partial derivative of f with respect to x plus the partial derivative of g with respect to y. My field is x squared plus y squared comma 0. So that will be 2x. That's the partial derivative of the f component with respect to x, plus the partial derivative of the y component. Well, the y component is 0. So that's just 2x. There's my divergence. And the flux form, here's where we are actually not going to use kind of the definition of the flux. We're going to use the differential form. It's practically just simpler to do. Okay, we need a path. We need a path. So let's take a look at the region here. The region is all the points such that x squared plus y squared is less than or equal to 1. So there's our region. So we need a path for the circle on the outside. Let me just kind of put that in a different color. Right, we need a path for that circle there. And so that's just the unit circle. And so I would just do cosine t sine t. Oh, the one thing we need to be careful of is make sure we have the right orientation. It must go counterclockwise. Conveniently, that's the way the unit circle goes. So that works out well for us here. So we can just use the unit circle structure as our path. Okay, so the way we're going to do this line integral, oh, I need a t here. T, to get all the way around, t would go from 0 to 2 pi. We're going to integrate from 0 to 2 pi, and then it's going to be the f component dy, so that's x squared plus y squared dy, minus the g component is 0 dx. This is kind of bad notation what I've done here. Maybe let me take the 0 and 2 pi off and just leave the c, because the 0 and 2 pi are t values. We will need them, but it looks kind of awkward right now to write them in when I have the dy and dx there. So maybe better to leave them off. And I'm sorry, it's a lot easier for me to erase than it is for you. Okay, so now what I need to do is convert this to a line integral. So conveniently, there's a 0 dx. So now I'm going to convert these all, but I have to convert them all to t's. So I'm just going to look at, well, what are x and y on this particular curve?
Wouldn't it be 1?
Yeah, right? Because x is cosine, y is sine. And so that's just going to be 1. And then dy is like the differential. If y is equal to sine of t, well, then dy will be cosine of t dt. And so, yeah, that is just the integral from 0 to 2 pi of cosine of t dt. Yeah, nice recognition there. And again, my Calc 1 students would say, all right, I could take it from here. The integrals are not usually the hard part on these. You get sine of t from 0 to 2 pi, which actually is 0. So this is the flux. How much of this field is flowing across the unit circle? And I have a good explanation why, by the way. I'll get there in a second. I want to do the other part too. Okay, that's the first integral. Now we want to do the double integral over the region of the divergence of the field, dA. So that's the double integral over the region of the partial derivative of f with respect to x plus the partial derivative of g with respect to y dA. Incidentally, I don't know if you'll get to the point where you'll be able to rattle these off like I'm doing. The only reason why I am is because it's the second time teaching the course and it's getting super familiar to me. It's not a class I teach very often. So don't feel bad if you have to keep referencing back to your formula sheet. Like, it's fine. It's totally fine. That's what I had to do last semester. This semester.
This is by far the hardest class I have taken so far. So.
Yep, lots of formulas. So reference that formula sheet. You don't want to lose points because you thought you knew it and then you wrote down the formula wrong. So, all right. We have the Flux or the divergence. It's up there, 2x, and we'll do. I guess we can do. Oh, you know what? I don't want to do dy dx. No, that's a bad idea. What should I do instead? Here's the region. This is the region up here.
Cylindrical or spherical? No?
You have a good thought. This is a two-dimensional integral.
Oh.
RD theta.
Yeah, what coordinate system is that?
That would be Cartesian.
Nope.
No, that's the one we're using.
Right.
Cylindrical.
Well, kind of. So cylindrical is the three-dimensional version of polar coordinates. That's what you're trying to think of. So you're right. It's RD theta. Yeah, it's polar. Yep. So cylindrical is just polar with a z. So they're the same kind of, but this is just a 2D integral. So I agree with Jacob. I would do that as well. I would do 2, and then x is r cosine theta, and then r dr d theta. And then r goes from 0 to 1, and theta goes all the way around 0 to 2 pi. So we have a 2 out in front, 0 to 2 pi, 0 to 1, r squared cosine theta dr d theta. Start to get a little nervous. I'm like, how is all of that going to give us 0? Because it should give us 0. This whole point is you're supposed to get the same, but it's going to be fine. So r cubed over 3 from 0 to 1, it's the cosine theta that's the key. And so that'll be 1/3 from the r cubed over 3, but you already have a 2, so 2/3 integral 0 to 2 pi cosine theta. And integral of cosine is sine from 0 to 2 pi, and again, we get 0. Yay, it worked. We got the same thing. Now this one is interesting. It asks you, why is there 0 divergence? Kind of at the end. Oh no, it doesn't ask you. I'm thinking of the homework question it did. But I would like to ask, like, well, why is there 0? Why is there no flux? Why is there 0 flux? Let me draw the region again. Kind of zoom in a little bit. It was the unit circle, the interior of the unit circle. In our field, if you recall, our field was x squared plus y squared, comma 0. So these are all horizontal vectors. In fact, they're all positive or non-zero, or non-negative, I should say. They can be 0. If x and y at the origin, it's the 0 vector. Everywhere else, it's non-zero and pointing to the right. It's positive. And what's interesting is on the unit circle, what is the field always on the unit circle? Keep in mind what x and y are on the unit circle.
1, 1.
Close. The y component is always 0, though. So because x squared plus y squared, remember your path was cosine t sine t. And so x squared plus y squared will always be 1. So if I were to draw the vector field just on C, not the whole vector field, but just on C, they would all be, these aren't to scale, they'd all be 1 to the right. On C, they're all 1 to the right. So if you want to know the net flux across it, well, on one side, they're all coming in. On the other side, they're all going out. So the net flux, 0. That's why it's 0. So anyway, that's what it means. That's what the flux means there. All right, any questions on this second example?
You mean the flux of the vector field, right?
Yeah, the flux of the vector field across the path.
Okay.
Yep. Yeah. You can think of the vector field representing like flow of water or something like that. And so if you have this, like, what are you like gaining or losing water? And here, there's no change. The amount of water coming in is the same as the amount of water going out. Any other questions on this one? All right, let me scroll down here. I think I want to make sure we hit one of every type. So I'm going to hold off on 46 because we did a circulation one, we did a flux one. So this is just another one of both. It's just a different region. And so I think we'll just maybe come back to that one if we have time. Oh, it's 5 o'clock already. Let's do 17.5. It's actually very quick. It's just two things. It's just divergence and curl. And so there's no integrals here in 17.5. And then let's focus on the second half. After the break, let's focus on 17.6. So let me open up the notes again. I really don't know why it like zooms out when I go over. So for 17.6, you have, oh, where's the divergence? That's first. The divergence, we make up this kind of makeup, but we kind of develop the idea of this gradient operator, where you have a vector whose components are partial derivative operators. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. So you'll notice this divergence is almost the same as the Green's theorem, except there's a z component also. And so the divergence is the dot product of the gradient operator with a vector field. And so what that means is you take the partial derivative with respect to x of the f component, add the partial derivative with respect to y of the y component, add the partial derivative with respect to z of the z component. That's the divergence. And then the curl is the cross product of that gradient operator. That one is a little, it's annoying when you have to do that. That's more work. So I would like to do an example of each before we take our break. Divergence is the easier one for sure. Divergence of the field is the gradient operator dot product with the field. So what that means is that's the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, dot product with our field, x squared y z, negative xy squared z, negative xy z squared. I'm going to write an extra step here. You would probably do this step in your head. But just to be clear, this means take the partial derivative with respect to x of the x component plus take the partial derivative with respect to y of the y component plus take the partial derivative with respect to z of the z component. So that's just 2xyz plus negative x squared z. Uh-oh. It says my internet connection is unstable. How can my internet connection be unstable? I'm hardwired. Let me know if I'm breaking up or anything if you start losing my signal.
No, you're good.
Yeah, it was weird. I just had this Zoom popped up with like your internet connection is unstable. Partial derivative with respect to z, negative 2xyz. Oh, those are opposite. So we get negative x squared z. All right, so that's the divergence. That one's not too bad. And again, it's all about question.
The middle one wouldn't also be negative 2 xyz?
No, because you're taking derivative with respect to y. And so the negative x squared and the z are treated as constants.
Oh, well,
So-
I'm looking at it. I'm looking at the function number 12 up in over in the middle.
Oh, I copied it wrong. I see. So I had it right in the first line, but then I didn't copy it right in the second line. So that one, you're right. Now with respect to y would be also negative 2xyz. Yes. Mm-hmm.
I got confused there for a second.
Yeah. No,
That's not what I
definitely.
got.
Right, and my brain just saw that too, like a little to the left. It just kind of shifted it a little to the left. Those are the ones where I see those on the exam where it's like, oh, like I just take a point off because it's like we all make those little mistakes. I totally knew what you were doing. The worst is when you make that little mistake and then all of a sudden the problem is not possible. That's the worst. Then I don't really know how to handle those. Those are really hard to grade. All right, that's divergence. Let's skip 16 because it's just another divergence one, and let's talk about curl. Ooh, we just have that one. Yeah, we do just have that one. Okay, so here's the curl. It is the cross product, and so this gets a little messy. We have to do I, J, K, and cross product of the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And then 3xz cubed e to the y squared, 2xz cubed e to the y squared, and 3xz squared e to the y squared. There is a formula in that section if you want that you are free to use. For me personally, I just find this cross product every time. It doesn't matter, it's the same thing. The formula is just this in general. You'll see it in there if you look at the end of 17. Where did it go? Here, it's this guy. So page 157, you can use, this is the same, this is just the general version of it right here. But I just always find the cross product, so. Okay, so we have I times, and then we're going to take the partial, we're going to do it this way, right? Partial derivative with respect to y of the bottom right. So that's 3xz squared e to the y squared times 2y. The partial derivative with respect to y. Minus the partial derivative with respect to z of the middle one. 6xz squared e to the y squared. Right, now erase that one, minus j, and here we're going to go, that's like impossible to read, but we're going to go partial derivative with respect to x of the bottom right. So 3z squared e to the y squared minus partial derivative with respect to z of the bottom left. 9xz squared e to the y squared. And then plus k. I was hoping it would erase all that. That was nice. So k will go this direction. Partial derivative with respect to x of the middle one, 2z cubed e to the y squared, minus partial derivative with respect to y of the bottom left, 3xz cubed e to the y squared 2y. Whatever that is, I am not going to bother simplifying that. Not much to simplify anyway. So that's the curl. It's the cross product of the gradient operator with the vector field. And that's really all there is from that section. So that's why that section is not too bad. There was a couple other things in there, but that's what I want you to get out of that. Can you find the divergence? Can you find the curl? Because they get used in 17.6 and 7 and 8. So that's why you just got to know how to find those. So I'm not going to ask a question on the final that says find the curl. I'm going to ask a question that uses the curl. And so you'll need to know, oh, I need to find the curl. So. All right, any questions on these two? All right, let's take a 5-minute break, which puts us at about 5:12. We'll say quarter after. And then if you think of some questions, feel free to type them in the chat and I'll kind of see them there when we come back. Otherwise, what we will be doing next is we will be looking at the 17.6 practice, which again is in D2O under the Unit 5 folder. There's some 17.6 extra examples and we will start with those. All right, have a good break. I'll see you 5:15. And step away for a second, and I have like 16 different emails here. Just gotta check one thing here. Oh, it's like way nicer today than I thought it was going to be. Tomorrow too, apparently. So I'm like putting my socks back on. I was outside in the grass. So I'm like, hey, I'm going to go outside, get some sun. I've not gotten any sun today. I've been grading away. I'm not looking forward to grading finals next week. Because usually they come in waves. So usually I don't usually teach night classes. So what I usually do is split the final into 2 parts and do like Monday and then Wednesday. So I'm kind of grading Monday, Tuesday, Wednesday. Now I'm like, your class, my other Calc 3 class, and my Calc 1 class all have a midnight deadline Wednesday. So Thursday and Friday are not going to be fun next week. That's all right.
You're only having 3 classes right now?
No, then I have a stats class too.
Ooh.
But their tests are pretty easy to grade, and they're actually just their class is so cumulative, and because of the craziness this semester, we're just going to do a 4th unit exam for them.
Okay.
So we're not going to do a final. Okay, so I don't see anything in the chat. I don't know if anyone has any additional questions they had. Otherwise, I'm going to just jump back in here to some 17.6. Anybody have anything they wanted to ask about? Okay, cool. All right. Let me pull up the notes from 17.6. So the topic is about surface integrals. The challenging part, at least for me, the challenging part is there's a bunch of prep work to get to before you can do a surface integral. And one of the prep things is we did this for line integrals where we had to parametrically describe the curve. So if I can get the curve described in terms of t, then I can just integrate in terms of t. Well, that works for a curve, but it doesn't work for a surface. There's no way to define a surface parametrically in terms of one variable. You can't trace out the whole surface. Think of a 3D printer. You can kind of like trace out a whole surface because it's back and forth. Well, you can't do that with a surface theoretically that's infinitely many little back and forth, right? So you need 2 variables. You need 2 variables to parametrically define a surface. So that was the first part of this section, is how do I parametrically define a surface? So I have the first couple of examples are, okay, here's some surfaces. How do we parametrically describe them? So let's take a look at the first one here. We have z squared equals 4 times x squared plus y squared for z between 0 and 4. And I should have plotted this one already. But let me do it right now. Implicit plot 3D, oops, z squared. I don't know, does anyone know what this thing is?
You said well, the x squared plus y squared is a circle.
Makes you think circle, right? There's
Yeah.
definitely a circle involved.
Is it more like cone?
Yes, it is. Yep. I think I need to go a little wider. Oh, shoot. What? Implicit plot 3D. So I had this the other day, but apparently sometimes Maple just doesn't like You have to like type it again. I don't know, I feel like that's what I had typed. It's interesting, it's having a hard time rendering this. So let me add some, it doesn't look like a good, let's do axes equal normal and number of points. Let's get it a big number here. Hopefully I don't crash my computer. Let's try 10,000. It's interesting how it still doesn't connect even that many points. Still can't connect it. So yeah, good call. It is a cone. You can actually see that if you do the like a trace. Like what if I do a some traces here like in the YZ plane. So if I let x be equal to 0, z squared is 4y squared. And if I take a square root, z is plus or minus 2y. And so I have these lines like that. And the same thing for x. You can get z is equal to plus or minus 2x. And then if you try some other constant z's, like say I pick z equal to 4. No, that's, z equal to 4. Like say I look at z equal 4. 4 squared equals 4 times x squared plus y squared. Well, that's 4 equals x squared plus y squared. There's that circle you were talking about. And you can see that on the graph. If I look from above, here is the circle. Do you see even the 2's there? Circle radius 2. That's the circle radius 2 when z is 4. I can put another one in here. What about when z is 2? Z plot 3D, z equals 2, x equals -2 to 2, y equals -2 to 2, style equals surface, color, let's do this one equals red. All right, what are the odds of me not making an error in Maple? Oops, I just need to, there it is. There it is, okay, so there's z equal 2, and that one's a little harder to see, but that one would be a radius 1. When z is 2, if you put 2 into there, into the function, you'll see that's a radius 1. So what we're making as we progress up is wider and wider circles as we progress up, wider and wider circles. So somehow I want to get this surface, this bluish surface here, I want to define it in terms of 2 variables parametrically. So one thing you might notice here with the circles, the x squared plus y squared is like maybe I could use polar coordinates. Is there a way I could use polar coordinates? So if I did that, x would be r cosine theta and y would be r sine theta. Okay. Well, then z squared would be 4r squared. So z, now normally we would do plus or minus here, but it's only positive. Do you know why it's only positive?
Because it's not going underneath the.
How do you know? And you can't use because that's what your graph shows, Professor Kernler.
Yeah, I was gonna say that, but no.
Boy, did you have an idea?
Yes, because z here is 0 to 4, so it cannot be negative, and because 4 is there's r squared, so it cannot be negative 2.
Yeah, very good, excellent. So good reasoning there. So the key is that 0 to 4, yep, says that our z can't be negative. So if you look at this now, we have x is our cosine theta, y is our sine theta, and z is 2r. Well now, x, y, and z are defined in terms of only 2 variables, r and theta. This is actually a parametric definition. We could stop right here. Because a lot of the formulas for surface integrals involve, are written in terms of u and v. So when we go to what a surface integral is, they're all written in terms of u and v. So typically what we will do then is we'll do a little substitution. You don't have to get rid of the r and theta, but then you'd have to say, well, hold on, that means I have to replace all these u's with r's, or replace all these v's with thetas. So what we're going to do is we're just going to do a little substitution. Whoops, I'm in the wrong. Where did it go? There it is. Okay. We're going to do a little substitution. We're just going to let u be equal to r and v be equal to theta. So then our surface is now parametrically a function of two variables, u and v, and it's u cosine v, u sine v to u. Okay. And if you were, this might seem a little weird here because this is r, this is a vector, and this goes back to the beginning of vector valued functions, chapter 14, 13, 15, and it's all blurring together. I think 13, vector valued functions, where yes, we're talking about a vector, but we're really considering the set of all of those terminal points. All of those terminal points of all those vectors are creating this surface. So you have to think of vectors that are all pointing around here, and together they're creating some surface. Now, we have one problem here that we still have to remedy. We have the entire cone right now. So we need some restrictions. We need some restrictions on u and v. I think v is the easier one here because
0 to 2 pi.
0 to 2 pi, right? Because you have to go all the way around. You have to go all the way around. So that's 0 to 2 pi. U is a little trickier.
It's not 0 to 4?
It feels like it should be. It is not.
Is it 0 to 2?
Yes, Jacob. How do you know?
Because if we set the z value equal to our restriction, then 2u cannot go beyond 4, so you can't go beyond 2.
Everybody catching that? So if you take our 2u and set that equal to 4, which is the maximum, oh, that means u is 2. That gives me the upper limit on 2. By the way, this parameterization, its domain should always be a rectangle. And now you're feeling like, Professor Kernler, you are just messing with me now. It's a cone. There's no rectangles here. It's a little mind-bending, but if we have the UV plane, and I consider the rectangle in the UV plane, every point in that plane corresponds to a point on that cone. Okay, that's what a parametric description does. It gives you a point in a 2D region, a set of points. It gives you a whole 2D region where every point in that 2D region corresponds to exactly one point on the three-dimensional shape, the surface. To be a little honest, I think I had to teach this class to understand that. I'm pretty sure I get it totally now. So there's going to be some stuff here that you're going to be a little fuzzy about, and that's natural. It's kind of a natural progression. It still doesn't feel good though.
Not at all.
No. For you, what I would do is kind of start making some notes of some of these parametric descriptions, because there's some trends, and there's some stuff that keeps coming up, and like, oh, here's how you parametrically define a sphere. Here's how you parametrically define a cone. And so there are some common ones that keep coming up.
And then we can use those for the surface integrals, right? Instead of having to figure it out for ourselves.
Correct.
Okay.
Yes. So in the videos, if you've watched all those videos, if you do, by the time you get to the last 17.6 one, I keep using parameterizations that I developed earlier. I think in the notes, I only parameterized 2 surfaces, and then I keep referring back to those for later examples. So you are welcome to have those in your, hey, here's the parameterization of a sphere. And then if you need to parameterize a sphere to do a surface integral for like flux across a sphere, you have the parameterization. Those problems are really hard to write for an exam because, like I said, if you've watched the videos, half the time I just kind of stop and say, okay, this would take another 15 minutes. I'm just going to tell you what the answer is. So they're really hard to write for exams. So we're either going to have really simple ones where the region is fairly simple, and so computing the parameterization and doing all that is simple, or we'll just have you like set something up, set up a surface integral that would do this, because the whole integrals there, it's not great. It's not good. Like I have.
Yeah, they're mammoths. They're huge.
Yeah, here's one. And then I didn't show all the work here. So I skipped finding the magnitude of that and just summarized it. This one we did all the way. I only made one error. That's the red. That was a full page. And then that one was not too bad. That was not too bad. And then the very last one, I remember some of these I think I did. Yeah, but then anyway, they're long problems. It's hard to come up with some that are reasonable to do as a test. Some of these would be much better as like project questions, something that you're like, yeah, 2 weeks to work on this. And it's just like at the very end of our course, even in a good semester. So we kind of just try to expose you to it and give you a couple to look at on the exam. Okay, so here we have a cylinder. Y is equal to, no, y squared plus z squared equals 36. So this is a cylinder along the x-axis. It's not a vertical cylinder. Right, and then come in, I don't know if I can draw another good one out here. Something like that. And this would be at 9. So it goes, x goes from 0 to 9. It's a cylinder along the x-axis. Its radius, oh geez, its radius is 6. That one should be really easy to draw and do in Maple. Famous last words. Implicit plot 3D. Y squared, or z squared plus y squared equals 9. X goes from 0 to 9. Y goes from -6 to 6. And z goes from -6 to 6. All right, there it is, right? Little clunky because Maples, that's the way. A little smoother. So there it is, right? Extends out 9 in the x direction. Oh, I did equals, why did I do 9? 36, I'm like, wait a minute, the radius isn't right. There we go, radius 6. Should be radius 6, that looks better. Radius 6, you can see the 6 looking down the x-axis, and then it goes out to 9 on the x-axis. Okay, so I feel like the previous one, we kind of used polar coordinates, but here we're still going to use polar coordinates, that idea, but they're not polar coordinates because it's not the x and y plane that we're basing it above. It's now the y and z plane. So I would do similar, like this is still a circle. So I would still do something like r cosine theta, r sine theta.
You're allowed to do that.
Right? It feels weird. It's like, wait a minute, whoa. So yes, because all we're trying to do is find a parameterization from it. But this isn't quite right. We have to modify what we have, but it feels like that, like it's a circle. So it feels like I should be able to use some version of polar coordinates. So this is okay. What I have written here is not going to work though. We need to modify it. does anyone know how to modify it? There's a key difference between number 14 and number 12.
You gotta isolate the z?
Nope.
Or no?
Nope, don't need to do that. Think about the key difference between this guy and this guy.
Yeah.
There's something about how the radius is changing.
Yeah.
Yes, right? The radius was changing on the first one, right? The radius was getting bigger and bigger and bigger, but on ours, the radius is just 6. So that's different. So we have to modify this and say, hold on, put a 6 there. So 6 cosine theta, 6 sine theta, and then x is just x. It's just x. I don't know. It's just moving in and out. And then y and z together are making circles. So when x is 1, there's a circle radius 6. When x is 1.8, there's a circle radius 6. When x is 2.76, there's a circle radius 6. So x is just moving out from 0 to 9, but y and z are together making all these circles of radius 6.
So in this type of equation, you wouldn't have a u, but only a theta?
Oh, you're going to have both.
You're going to have both?
Because I have 2 variables here. Now there's the obvious one, theta. What's the other variable? What's the other thing that's changing?
It should have been r, but it's not changing anymore. So.
Nope, it's not, right? Correct, it's not r.
It's x.
It's the x, yeah, because you're just moving along the x-axis. So you got to be able to move along the x-axis. So you can pick whichever one you want to be u or v. It doesn't matter. So let's let x be equal to u and theta be equal to v. So then we have x equals u, y equals 6 cosine v, and z equals 6 sine v. You could switch the u and v here. It doesn't matter. It doesn't matter at all. So my parameterization of u and v in terms of u and v would be u 6 cosine v, 6 sine v.
From
Ooh, yep.
0 to 2 pi, no?
For which one?
V.
For v, yep.
Yep.
We need to go all the way around the x-axis, which feels weird. But it's the x-axis we're going around, right? That's here, right? Here's the x-axis sticking out, so we need to go all the way around the x-axis. That's the 0 to 2 pi. And then what about for u?
I would like to say 0 to 9, but
yeah,
I'm
yep,
not sure.
Yep, Jacob said it too. Yep, you're both right. 0 to 9, because that's the x. You're coming out the x-axis. So that's 0 to 9. Uh-oh. You all are lagging, and then it's still saying my internet is unstable, so I don't know. So that's part of it. You gotta have.
Now you're lagging a little bit, not a lot, but you are.
I wonder if, I don't think I'm on the Wi-Fi though. No, see, I'm on the network.
Now it says my connection is unstable.
I don't know.
Oh no, I think that's just share screen. Never mind, I'm sorry.
I don't know. Because I'm not even on the Wi-Fi. I'm connected to the hardline network, so maybe the internet is exploding here. Who knows? Okay. All right, we have about 20 minutes left. And I think I had 2 questions here. A surface interval of a vector field, surface area. Okay, I think let's try this one. Let's try 22. Okay, this, just fair warning here. I kind of grabbed these as examples. Unlike the problems in my notes, I have not done these yet. So we'll see, this will be a good experience for us to kind of try it together. So we have a hemisphere. We're going to need to parametrically define a hemisphere. You can see it's like rho squared equals 10 squared. So it's a hemisphere radius 10. And we're going to try to find the area of the surface. So you can think of, when you want to find the area over a region, you're just integrating over the surface, and we should have a formula here. Surface integral right here. Oh, nope, that's explicit ones. We don't have explicit ones yet. So it's this guy right here. Let me see if I can grab this. Kind of use this as a reference. Oh, it's not letting me just paste in there. Whoa, really big. So we're going to do a surface integral, but if we just want the actual area, then our function will just be 1. Okay, so our function in here is just going to be 1. So what we're going to need to find is we're going to need to find the double integral over the region of the cross product of these tangent vectors and the magnitude dA. So we're going to have to find a parametric description of R in terms of U and V. Then we'll need a tangent vector in the U direction, which will be the partial derivative of R with respect to U. We'll need a tangent vector in the V direction, which would be the partial derivative of R with respect to V. And then we'll need the cross product of those. So that's the stuff that we're going to have to do. Put that stuff over here. So this is the point we made earlier where like, okay, we can make a note of some of these kind of similar parameterizations. And if we go back to the notes, we did do a sphere. Somewhere in here, there is a sphere. Well, we can use this guy right here. This is a cap of a sphere, but it's basically using spherical coordinates. But I think we even have some more information from a sphere. Yeah, we're going to refer to example 5 here. Okay. This is annoying that it like resets and I have to restart every time. Deep breath. Technology issues here. It's been a long day. I don't know how you all who are, like most people, I should say most people, on average, you're more likely to have students who work or are taking night classes. During the day, you have students who generally work a little bit less. So I don't know how, I've thought about classes that I've taken while I'm working now. I'll take a class at NAU once in a while. And it, the workload isn't too bad, but it's not like Calc 3. So I don't know how those of you who are working full time are like still maintaining the mental energy to try to also try to learn as much of this as you can. So the parameterization.
I work full time and I take 3 classes. It's just brutal.
Brutal. So I'm gonna cheat a little bit and use. It's just too hard in there to flip back and forth. It's just not working for me. So I'm gonna just pull out the notes, the paper notes that I have here. So from example 5, I think it's on page, or example 3. For a sphere, you can have the radius of the sphere, and ours is 10. So 10 sine U sine V, 10, nope, that's Y. Cosine V, 10 sine u sine v is y, and then 10 cosine u is z. And let's see here, if we wanted to get the full sphere, the u here is representing phi. And v is theta. So if we do the full sphere, we would go from 0 to pi on u, that would get the full sphere. And theta would go from 0 to 2 pi, so v would be 0 to 2 pi. But we just have a hemisphere here. So let's go up and take a look here. Z greater than or equal to 0. So that's
Pi
going
over
to
2 to 2 pi? I mean, pi over 2 to pi?
close. That was the exam one. On the exam, it was the two of them, and it was below the xy plane. So as you're coming, that's pi over 2 to pi, but we want the top half here. So we're going to go 0 to pi over 2. So we're going to do that, 0 to pi over 2. And I'm going to write out a couple things here, and you can look back at that page. This is actually, it is example 5, page 165. We have some limited time left, so it's not super worth our time to do all of this, but just to kind of tell you how it's built up. So the tangent vector in the u direction is just taking the partial derivative of this r vector with respect to u. That's 10 cosine u cosine v, 10 cosine u sine v, and then negative 10 sine u. This part is not bad. Just some partial derivatives. The tangent vector in the v direction, partial derivative of r with respect to v. Let's see, negative 10 sine u sine v, 10 sine u cosine v, and then 0. Nice. This is one, ironically, these problems. The calculus is actually the easy part on these. The hard part now is, now I need to find the cross product of those two vectors. Did not leave myself enough space. Gotta move down a little bit. Not only that, I have to find the magnitude of the cross product of those two vectors. So I'm writing in all the components of these vectors. And you can see why. We'll try to come up with some examples that either use these same ones, these same parameterizations, or the parameterizations are very simple, because finding these cross products becomes very tedious. So I'm gonna just put a little note here. See example 5, page 165, and I'm just going to write down what the magnitude ends up being from that example. And the magnitude just ends up being, it's crazy after all that. Can you imagine finding that whole cross product, and then you find the magnitude of the cross product, and it's just the radius squared sine u? It's nuts. There's a lot of trig identities in there. A lot of Pythagorean theorems. Pythagorean theorems, sine squareds plus cosine squareds. But for our purpose now, we want to find the surface area. That's the double integral over the region of 1 times the magnitude of this unit, the cross product of these unit tangent vectors, dA. And the region that I'm talking about here in the dA, it's in the UV plane. It's that rectangle in the UV plane. So this is the integral of 100 sine u du dv. And then this is where you need your rectangle up above. U goes from 0 to pi over 2. V goes from 0 to 2 pi.
Why do we set the function equal to 1 in the
That
integral?
just, yeah, so that's a good question. When you have a surface integral, you're kind of adding up a function over the area, the surface. If your function is 1, what you're adding up is you're just getting the area. And so this question was just find the area of the surface. So it's very specific only if you're asked for the surface area that the function is 1. Does that answer your question?
Yeah, thank you. So if we're finding like volume or something, then we have the equation.
So you would not be finding a volume with the surface integral. What you would be finding is you have to have some function that varies over the surface. The example I did in the notes was temperature. So you think of the Earth as kind of a sphere. It's not really a sphere, but it's close enough. And if you have a function for the temperature on any point on the Earth, you could find the average temperature. So you could add up all of the temperatures, which is the surface integral, and then divide by the total surface area. And that would get you the average temperature. So you have to have some function that has some meaning that you're adding up over that surface.
And that's when you use a function instead of 1.
Correct.
Okay.
Yep. And more applicable to the last couple sections is when you have a vector field and you're trying to find flow. Remember we were doing the circle, how much is flowing, the flux across that curve? Well, now we have a surface and we have some field that's flowing. And so how much of the field is flowing across a surface? And that's the last video in 17.6. That's surface integrals of a vector field. And that kind of becomes the function then. That vector field becomes part of it. It doesn't just become the function, but it factors into what that function is that you're integrating right here. So that's really the goal. That's really the end goal. My primary goal for tonight and for the last couple of videos that you're going to watch and for Monday is, so in the future, when you're exposed to something like a flux integral and you're thinking about that concept and you're talking about vector fields, that you kind of have a grasp on what these things mean, because the amount of content we're trying to do in 2 weeks, it's like not humanly possible. And so I'm not going to expect that you've mastered this content and you have to have this content mastered to pass this class. That might, honestly, I think it's going to happen for a few students. But it's not like my goal for everyone. I want us to really be comfortable with those concepts. That's really my goal.
What future courses do you see, do we see these integrals?
So that's a very difficult question for me to answer, and I'll tell you why. So I was not an engineer. I was gonna, actually I thought about it. I studied that for a while, and then I just went pure math. And the math classes that I took, I didn't do a triple integral since after Calc 3. And I did not integrate vector fields over surfaces. But I was like a pure math, and like that just wasn't, it's like a physics application. So for me, I don't know the exact courses when you're doing these integrals, and the more I teach this class, that's something I should really know. Oh, you might see this in this engineering class. I think it's going to be the engineering classes. That's where you're going to see this.
Yeah, I'm trying for computer engineering, which I don't think it's going to have that.
Probably not. Mm-mm. maybe some electrical fields. There might be some electrical engineering classes you have to take there, and it might be something in there.
Yeah, it's a hybrid of computer science and electrical engineers. So
Yeah. I'm just speculating though. Let's see here. So this integral is pretty straightforward. This is 100 times negative cosine u from 0 to pi over 2. That's still dv. Cosine of pi over 2 is 0, minus cosine of 0 is 1. And so what do we get here? We get just 100 integral from 0 to 2 pi dv, which will be 200 pi. I feel like we're missing something.
That's what I got.
Yeah, so I'm trying to think of the actual surface area. No, I think that's right. So the surface area of a sphere is 4 pi r squared. And we have a hemisphere, so ours should be 2 pi r squared, yeah, which is 2 times pi times 10 squared. Clearly the surface integral is not an efficient method to calculate the surface area of a sphere. But of course, this presumes that you know the formula for the surface area of a sphere. A surface integral could be used to derive that formula. All right, we only have a few minutes left. I think we do have time to actually set up this last one. We're not going to be able to find the parameterization and find the TU, find the TV, find the cross product, find the magnitude. That's not possible. But I'd like to at least look at the flux of a vector field across this surface and what that looks like. So that's another formula at the end of the section 17.6, excuse me. Well, we don't actually need to find the magnitude here with this one. Ooh, this one is z is cosine y. So I need the other one. This one is if you have a surface that's defined parametrically, but here we actually have a surface that's defined explicitly. Oop, not that, sorry. So we can do this one. So this might actually be easier than the previous one because we don't need to find a parameterization when the surface is z is a function of x and y. So what these are these integrals I was talking about where you're finding the flux across the surface. So you have some field, it's water, it's electricity, it's magnetism, there's some field, and how much of that is crossing perpendicular to normal to the surface. That's what this is. So you'll see this dot product, the field with a normal vector. So that's that flux across it. And if you have, as we do here, z is given to you explicitly in terms of x and y, in this case only in terms of y, then you can find that surface integral using this handy dandy formula here on the right, which is derived in the notes. It's essentially those partial derivatives are there because of the derivation of that normal vector. Okay, so we just need our region. This is actually easier than I thought. It's the field e to the negative y 2z xy dot product with the partial derivative of x of z with respect to x. That's 0. The opposite of the partial derivative of z with respect to y. So that will be sine y, and then 1. dA. Well, that's not that bad. That's just 2z sine y plus xy. That's not bad. So the reason why we didn't need the u and v and all that here was because the surface was given to us as a function of x and y. And so we could just use x and y and just have a rectangle. You'll notice, I don't know if you notice here, but this is a rectangle. Absolute value of y less than or equal to pi, x between 0 and 4. And so that's, you can just do dy dx. Y goes from negative pi to pi, x goes from 0 to 4. So this one, we have this surface above the plane, and we're finding the flux across this surface. And because the surface is given to us just as a function of x and y, you don't need the parameterization. Basically, the parameterization is x is x, y is y. You don't need to go through all this other derivation of unit tangent vectors and cross products and magnitude and all that. So we'll stop there. We don't have time to do that, but that's a pretty, wait a minute, we have a problem here. Oh, I see what it is. Okay. The problem is, I noticed the z here. Oops. We can fix it though, quick fix. Does anyone know how to fix the z?
Set it equal to cosine y.
Right, because we know what z is. Z is cosine y. There we go. That looks better. I was like, hold on. I just glanced over and saw that. Wait, that's not good. Okay, so now it's just a double integral. You could all do this double integral. It's not trivial, but it's not a super hard double integral. I don't know about you, but I am hungry, and my wife doesn't always cook, but she did cook something tonight. I can smell a HelloFresh pasta meal in the other room. So we are in the final push. I know you are all busy, and I do still have some free time in my schedule tomorrow and Friday. So if you're feeling like you want to maybe go over your exam with me, or you have some other questions you want to talk about with me, we can do email. That's fine. But if you wanted to do a one-on-one chat, we'll find some time. There's definitely time in my schedule for that. So feel free to reach out. Reminder, we are going to meet on Monday next week. Monday, not Wednesday. Monday, and we'll go over some homework questions. We'll go over
at 4?
Same time. Yep, 4 to 6. Yep, 4 to 6. We'll go over the quiz. I'm going to post this quiz tomorrow morning over 17, 4, 5, and 6, and we'll try to keep those on the lower end, right? Not some of they get a little crazy in there, so we'll try to keep those manageable. And then we'll try to talk a little bit about the last couple of sections, basically just to kind of plant those seeds for you so you kind of know what those ideas are. We're keeping our expectations low, not because you're not capable of it, but because of the situation. Okay, any questions at all before we log off?
Nope. Have a good night.
You too. All right, everybody, you know how to get a hold of me. Let me know if you have any questions. Have a great evening. We'll see you Monday.